Alright, good morning. Today we're going to continue on with the second half of section 14.3, one-sided limits, continuity, and we're also going to talk about limits on trig functions. So this first example, we want to know where is this function continuous. So again, we're going to create the graph so you can kind of see this a little bit better. Alright, so we're going to recall from earlier in the semester, we looked at these rational functions, and in order to graph them, we were looking for certain characteristics. Okay, so again, one of the ways you can find these characteristics was by factoring both the numerator and denominator. So that's what I did here. So I took this original function, I factored GCF in the denominator. Notice that I had common factors. Alright, so again, those common factors mean that there is a hole in the graph of this function. Okay, so we know for sure that we're going to have to determine where the hole is for this function. Again, when you cancel out the common factor, right, we know that when we set that common factor equal to 0, that the x value, the solution for x is where that function is equal, where the hole is in that function. Okay, so we know for a fact that the hole's x coordinate is at 0. Right, so to find the y coordinate for the location of the hole, we're going to plug 0 in for the remaining parts of that function. So if I plug 0 in for x, I get 1 over negative 4. So there's the location of the hole. Alright, so then we look at the reduced version of the function, and here we know that there are values of x that make the denominator 0, so there are going to be vertical asymptotes. Okay, so finding the vertical asymptotes, and what x values make the denominator 0, well, x equals negative 2, x equals positive 2, and we go back to the original function. There's also a, although since we have a hole there, actually, then we're not going to have a vertical asymptote for x equals 0. Okay? Alright, so the last thing we need to figure out here is the horizontal asymptote. Okay, so again, we look at the original function because the degree of the denominator is bigger than the degree of the numerator. And we know that our horizontal asymptote is at y equals 0. At y equals 0. Okay, so let's go ahead and graph what we have so far. So we have a horizontal asymptote at y equals 0. So y equals 0, so there's our horizontal asymptote. Vertical asymptotes at x equals negative 2 and at 2. So at 2 and negative 2, we have vertical asymptotes. Alright, and we have a hole at 0, negative 1/4. So negative 1, so there's a hole right here. Alright, so again, when we test values, we find out that, alright, so we have this part of the graph going on. Again, testing values, we find that we have our graph parts happening like this. Again, so the way we're finding this is to remind you that we're just going to plug in values. Like, for example, you plug in negative 3 in for x in the original function, find a value. Plug negative 4 in for x, find output values. And same thing over here. Right? So when you find certain values, you can kind of tell what's happening with the graph. Alright, with those values. Okay, so now let's go ahead and take a look at this function. Alright, the limit as x approaches negative infinity for this function. So looking at our graph, as x goes to negative infinity, this function is approaching an output value of 0. Right. Finding the limit of this function as x approaches positive infinity. And looking at the graph, again, it's all about end behavior. as x goes to positive infinity, this function output is approaching 0. Alright, so then let's look at the limit of this function as x approaches -2 from the left. So here's -2 coming in from the left. The output of this function is approaching positive infinity. So that's there's our limit. The limit as x approaches -2 from the right. So coming in from the right of -2, that's going to be this part of the function graph. And this one looks like it's going to an output of -infinity. Finding the limit of the function as x approaches +2 from the left. Here's +2 coming in from the left. With this graph, part of the graph, and that's going to -infinity. And the limit as x approaches +2 from the right, and that's going to be this part of the graph coming in from the right. Alright, that limit is going to positive infinity. Okay. Alright, so going back to the original question, where is the function continuous? Alright, so the function is continuous at all except at x equals 0, -2, and 2. Okay. Alright, so now we're going to look at example number 2, where given this piecewise function, we want to determine if the function is continuous at a c value of 2. Okay, so now you recall, if you look back at your notes from last week, right, there are 3 requirements for a function to be continuous at a very specific value. Okay, so one of those requirements is that the function is defined, right, at that c value. Okay, so I'm going to take this function, I'm going to input 2 in for x. So when I plug 2 in for x, according to this part of the piecewise, right, with an input of 2 into the function, the output is 2. Okay, so therefore we know that for sure that this function is defined at c equals 2. Okay, so function, right, is defined at c equals 2. Alright, because we had an output. Okay, so the second requirement is that the function has a limit from the left and from the right of that c value. Okay, so we want to find the limit as x approaches 2 from the left. Alright, so we want to see what happens when coming in from 2 on the left. So for this function, so to find that limit, so we take a look from the left, means we got x is less than 2, so we're looking at this part of the piecewise. Alright, so we're looking for the limit as x approaches 2 from the left of x squared minus 2x over x minus 2. Alright, so again, using our knowledge of these properties from last week, so we're going to take the limit, so we're going to plug 2 in for x in the numerator, so we got 4 minus 4, which is 0. And we plug 2 in for x in the denominator, so we get also 0. Alright, so here the limit, right, currently does not exist. However, this is factorable, so we're going to go ahead and factor this. Cancel that like factor. So now, when we plug 2 in for x, we get 2. Okay, so we'll cross that out. So the limit as x approaches 2 from the left is also 2. Now we want to find the limit as x approaches 2 from the right. So coming in from the right, we're looking at this part of the piecewise. So again, the function. So the limit as x approaches 2 from the right, x minus 4 over x minus 1. So we plug 2 in for x, we get negative 2. Right, we plug 2 in for x, we get 1. So here the limit from the right, coming from the right of 2, is negative 2. Right. So the limits do exist from both the left and the right. So now the third requirement is that the limit coming in from the left must equal the limit of the function coming in from the right. Well, coming in from the left, the limit is positive 2. Coming in from the right, it's negative 2. And because they are not equal, the limit on both sides is not equal, that means that this function is not continuous at a c value of 2. Because it does not satisfy the third requirement where the limits coming in from both sides of the function at that c value, they are not equal. So it is not continuous at that c value. Okay, so for this last page, we're going to look at some limits for functions that involve trig functions. So right here, we have, again, some function graphs that I got from my calculator. Right, so again, here we know that the limit as x approaches 0 for the sine function is 0. The limit of the function as x approaches 0 for a cosine function. Again, we approach 0 from the left and the right. The output value is 1. The limit as x approaches 0 for this tangent function. Again, we look at the tangent graph, and as we approach 0 on the x-axis from the left and the right, we do have an output of 0. So the limit is 0. Again, for these next few functions, again, just graphing these on a calculator. That's all I did was enter these functions in the calculator. And we figure out the limits for sine x over x is equal to 1. Coming in from the left and the right, it goes to 1. For cosine x over x, the limit of the function is x approaches 0, getting closer to 0. Since they do not have a common value, that limit does not exist. And for tangent x over x, the limit of that function is x approaches 0. And looking at the graph from the calculator, coming in from the left, coming in from the right, we approach this value of 1. Okay, so with that, we should be able to kind of use some really cool substitution in terms of finding these particular limits for these functions. Okay, so here's where we're going to use some substitution. So in the numerator, using an identity from that unit where we talk about trig identities, and I rewrite sine of 2x as 2 sine x cosine x. So now we're trying to find the limit of this function. So again, using one of those limit properties, we can break this up as the limit as x approaches 0 of 2 times the limit of this function as x approaches 0 of sine x over x. So grouping these together and finding the limit as x approaches 0 for cosine x. So the limit of a constant is just that constant. The limit of the sine x over x, we know from here, is equal to 1. And the limit of cosine x as x approaches 0 is 1. So multiplying all those together, we get a limit of 2. Alright, for this next problem, we're going to do a little substitution. We're going to let theta equal 4x into this function. So when we do that, we have and we're going to change x as x approaches 0 to as theta approaches 0. So we're going to do the limit as theta approaches 0 of sine theta over theta. Okay, very similar to this property above, that limit is equal to 1. Alright, again, finally for this last one, I'm going to go ahead and factor out the denominator. Again, do a little reworking or reorganizing of the parts of that function and using the different properties. to find the limit of this function, and which ends up to be negative 1/2.